I'm Dr.S.Prasanna, Assistant Professor of Mathematics, Pingil Government College for Women, Warangal. Today I want to deal with the first topic of Unit 1 in the subject in the paper Linear Algebra for the BSc final year Mathematics. The first topic of the Unit 1 is vector spaces and subspaces. Now, what is a vector space? Let us see the definition. If V is a non-empty set of objects called vectors and R is a set of all real numbers called scalars, that means we are taking two sets. One set V, capital V, which is a non-empty set consisting of all vectors, and R is another set which consists of real numbers and which we call them as scalars. Then V is said to be a vector space over that R, and it is denoted by V over R or simply V. If two operations called addition and scalar multiplication are defined on the set V and satisfy the following axioms. The two operations, namely addition and scalar multiplication in the set V over R. If those two operations satisfy the following axioms, then we say that V is a vector space over R. Okay, let us take two vectors in V, three vectors in capital V and two scalars from capital R, and let us see how the axioms go. First five axioms come under the subtitle axioms of addition. And what are those five axioms which come under axioms of addition? Let us see. The first property goes like this. The sum of u bar and v bar, denoted by u bar plus v bar, is in V. What does it mean? U bar, V bar, we are saying that U bar and V bar are two vectors in capital V, and still we can see that their sum U bar plus V bar is again belonging to the same set V. That means the set capital V is closed under addition. We can say that the closure axiom with respect to addition is satisfied in capital V. And the second axiom says that U bar plus V bar plus W bar is equal to U bar plus V bar plus W bar. This axiom is called associative axiom with respect to addition. So, if the associative axiom with respect to addition is satisfied in the set V, then two properties, first property closure axiom and the second property associative axiom, both with respect to addition, if they are satisfied in the set V, then the first two properties of vector space will be we say that the first two properties of vector space are satisfied in the set V. Now let us see what is the third property. There is a 0 vector 0 bar in V such that U bar plus 0 bar is equal to U bar, and we can say further it is equal to 0 bar plus U bar. That means U bar plus 0 bar is equal to U bar, which says that 0 bar is acting as additive identity. That means the identity axiom with respect to addition, this is called the identity axiom with respect to addition, and 0 bar is called the 0 vector in V, and by 0 vector we mean that is the additive identity in V. And next, fourth property says that for each U bar in capital V, there is a vector minus U bar in V such that U bar plus minus U bar is equal to 0 bar, or it is further equal to minus u bar plus u bar. That means minus u bar is acting as minus u bar, which is also again a vector in capital V, is acting as the additive inverse for the vector u bar in V. So the inverse, this is called inverse axiom with respect to addition. And the fifth property says that u bar plus v bar is equal to v bar plus u bar. That means this is called commutative axiom with respect to addition. So these 5 axioms come under axioms of addition. And what else the properties exist to fulfill the set V to be a vector space? Let us see. There are 2 more subtitles. The next one is axioms of scalar multiplication. There are 3 axioms under this title and under this subtitle. And what are the 6th property, 7th property and 8th property come under this axioms of scalar multiplication. And what are they? Let us see. The scalar multiple of u bar by a scalar c denoted by cu bar is in V. That means the scalar multiple of u bar is the vector in V, and we are multiplying it by a scalar c, and if cu bar, which is called scalar multiple of u bar by c, if that vector cu bar again belongs to the same set V, then we say that the scalar multiplication exists in V, or we can say that V is closed under scalar multiplication. And the 7th property says that 1 dot u bar is equal to u bar. 1 dot u bar is equal to u bar, and that is the 7th axiom in the vector space definition. And the 8th property says that c times du bar is equal to cd times u bar. This is also a property which comes under scalar multiplication axioms. And here we can see we are multiplying with 2 scalars, first one scalar and then with another scalar, and we can see that the product of 2 scalars together, that product is multiplied to u bar by scalar multiplication, and this is given as c times du bar is equal to cd times u bar. And the last subtitle is distributive axioms, and this constitutes of 2 properties, namely distributive laws. And what are those distributive laws? Let us see. In the 9th property, it is said that c times u bar plus v bar is equal to cu bar plus cv bar. That means scalar multiple of addition of 2 matrices is equal to addition of the scalar multiples of u bar and v bar with with the scalar c. So c times u bar plus v bar is equal to cu bar plus cv bar. And the last 10th property says that c plus d times u bar is equal to cu bar plus du bar. This means here in the 9th property we have taken 2 vectors, addition of 2 vectors multiplied by a single scalar, whereas in 10th property we can see that a single vector is multiplied by the sum of 2 scalars, and this is also, we can see it is distributive. So 9th and 10th properties are the distributive axioms. So on the whole there are 10 axioms, so which are among which first 5 axioms constitute the axioms for addition, and 6th, 7th, 8th, the 3 properties constitute under the axioms of scalar multiplication, and the last 2 axioms, 9th and 10th, come under distributive axioms. So if these 10 axioms are satisfied in a set non-empty set V of vectors over another set of scalars which is R, then we say that set V over R is called a vector space, is said to be a vector space, and we denote it by V over R, like this, V over R. If all these 10 axioms are satisfied, then we say that the set V over R is called a vector space, and we denote it by V over R or simply V, because the real numbers R is the common, very usual thing of scalars, set of scalars. Next, let us go through some remarks which can be drawn from above definition of vector space. And what are those remarks and what are the points to be noted down? First point says that axiom 1 above means that V is closed under the operation addition. That first axiom above in the definition of vector space, the first axiom means that V is closed under the operation addition. That means by the first property, the set V is satisfying closure axiom with respect to addition, and that is how it is closed under the operation addition. And the second note point says that axiom 6 above in the definition of vector space, the axiom 6 means that V is closed under the operation scalar multiplication. That means by the property 6, by the axiom 6 in the definition of vector space, we can say that the set V satisfies closure axiom with respect to multiplication. That means not closure axiom with respect to multiplication, we can say that it is satisfying scalar multiplication definition. That is how V is said to be closed under the operation scalar multiplication. And the third note point says that axioms 1 to 5, all the 5 axioms, the first 5 axioms of the vector space definition mean that V comma plus is an abelian group with 0 bar as identity and minus U bar as inverse of U bar in V. So first 5 axioms of the definition of vector space constitute the definition of an abelian group under addition, and hence the first 5 axioms show that V comma plus is an abelian group, wherein the zero vector 0 bar is the additive identity and minus U bar is the inverse element of U bar under addition in the set V. Now the fourth note point says that the nature of operations of addition and scalar multiplication depend on the nature of elements of V. So we cannot always say in generalized way that usual addition is the addition operation and usual multiplication is the scalar multiplication operation. Sometimes they may vary depending upon the sets we have considered for the set V. So if we change for different sets, then the operations may change, and depending upon the operations, the above definition of vector space can be changed according to the addition and scalar multiplication operations that are considered in the new set V. Now the fifth note point says that usually a vector represents a directed line segment. Usually the definition of vector always means a directed line segment. A line segment, part of a line which has some direction. But now in the vector space, we don't mean by a vector as a line segment always. The vector space in linear algebra, by the word vector space in linear algebra now onwards, we simply mean that it is a non-empty set which may be a set of n-tuples or a set of matrices or a set of functions or a set of sequences, or it can even be a set of vectors. So or even it can be something else also. So by the meaning of vector space in linear algebra is not just the directed line segments set, but it is sometimes the set of n-tuples, and sometimes it may be a set of matrices, or we can be a set of functions, or we can be a set of sequences, and we can even be a set of vectors also. So this is how the vector space notion we can understand in the context of linear algebra. And examples, I want to give some examples for vector spaces. Let us see the example 1. Here what I have done is, in the examples I am quoting some more examples also, but in the example 1 whichever I am taking, in that I have verified all the vector space axioms, whether that set over the given set of scalars is satisfying all the axioms of vector space. I have seen by verifying axiom by axiom in this example. So let us see what is that example I have taken as the first one for a vector space. I have taken it as R3. R3 is the three-dimensional vector space, the three-dimensional space of real numbers. And we have already come across with the set R3 in prerequisites topic 1. So R3 is the set constituting the elements of the form x1 ordered triads. They are ordered triads, and they are like x1 comma x2 comma x3, which is an ordered triad wherein each coordinate or each element is taken from the set of real numbers. That is how R3 is taken as set of all elements of the form. R3 consists of set of all elements of the form x1 comma x2 comma x3 such that x1 comma x2 comma x3 belongs to capital R. Now let us verify the axioms of vector space for this R3, and I have taken in this example I have taken the set of scalars as the set of real numbers capital R. So we have in place of V, instead of V, we are having the set R3 in this example, and in place of the set of scalars we are having the set capital R of real numbers. Now let us see the axioms, whether they are satisfied in this R3 over R with respect to addition, usual addition, and scalar multiplication. Now I am taking to verify the first axiom, I have taken it as step 1. And I have considered two elements from R3 and which are denoted by u bar comma v bar. If these vectors u bar comma v bar are in R3, then each of them should be an ordered triad. That is how I have taken two ordered triads for u bar and v bar. U bar is equal to x1 comma x2 comma x3 comma v bar is equal to y1 comma y2 comma y3. Here we can say that x1 x2 x3 and y1 y2 y3, all these numbers are nothing but real numbers, are the elements from the set capital R. Now let us see what is u bar plus v bar. U bar plus v bar, by the definition of addition of vectors in the set R3, we can write u bar plus v bar is equal to x1 plus y1 comma x2 plus y2 plus comma x3 plus y3. And we can also claim that u bar plus v bar belongs to R3. How can we claim this? It is by the reason that x1 plus y1 comma x2 plus y2 comma x3 plus y3, all these are real numbers. All these are taken from the set R, because all these belongs to capital R, because x1, x2, x3, y1, y2, y3 belongs to R, and that is how the sum of two numbers is again in R by the closure axiom with respect to addition in the set R that we have seen in the prerequisites topic 1 about the set R. So hence the axiom 1 of vector space is satisfied by R3 over R. Now step 2. Let u bar comma v bar comma w bar belongs to R3. Now I am taking 3 vectors u bar, v bar, w bar in R3, so that as they are in R3, all of these 3 vectors should be ordered triads. That is how I have taken u bar as x1 comma x2 comma x3, v bar as y1 comma y2 comma y3, and w bar as z1 comma z2 comma z3. Now I want to verify the second axiom of the definition of vector space, which is the associative axiom with respect to addition. That is why I have taken the term u bar plus v bar plus w bar here, and we can see u bar plus v bar by the above step 1. We can write it as x1 plus y1 comma x2 plus y2 comma x3 plus y3, and plus w bar means plus z1 comma z2 comma z3. Again by applying the same step 1, which is the addition of two vectors in the set R3, which is the definition of addition of two vectors in the set R3, we can write in the next step as x1 plus y1 plus z1 comma x2 plus y2 plus z2 comma x3 plus y3 plus z3. All these 3 elements are from the set R by the definition of R3. Therefore, these elements are in the set capital R, and we know that the set capital R is associative under addition. The set capital R is associative under addition, and hence I can write each element in this ordered triad as x1 plus y1 plus z1 comma x2 plus y2 plus z2 comma x3 plus y3 plus z3. Now by the definition of addition of two vectors in R3, I can split this into two vectors, sum of two vectors, and which are x1 comma x2 comma x3 plus y1 plus z1 comma y2 plus z2 comma y3 plus z3. Now we can say that it is nothing but equal to u bar plus v bar plus w bar. So now we could prove that the associative axiom with respect to addition, which is the second property in the definition of vector space, is satisfied by the set R3 over the set R of scalars or real numbers. Now let us move on to the step 3, wherein we have to verify the axiom of identity with respect to addition. And for that we need an element which acts as an additive identity in R3. we can see that for the number 0 belongs to capital R, that means for the real number 0, the ordered triad 0 0 0, which is denoted as 0 bar, belongs to R3, and that means an ordered triad with all the elements as zeros belongs to the set R3, and we are denoting that vector by 0 bar. Now we can say that u bar plus 0 bar, that is x1 comma x2 comma x3 plus 0 0 0, by the definition of addition of two vectors in R3, in the set R3, we can write it as x1 plus 0 comma x2 plus 0 comma x3 plus 0, and this is nothing but equal to x1 comma x2 comma x3, which is u bar. That is how we could prove u bar plus 0 bar is equal to u bar. Even if we want to show, we can also show that 0 bar plus u bar is equal to u bar. That is how the axiom 3 of vector space is by the axiom 3 of definition of vector space is satisfied by the set R3 over the set R of real numbers. Now let us move on to the step 4, which gives the axiom of inverse axiom with respect to addition. Let us take a vector from R3, which I have taken as u bar, and u bar here is equal to x1 comma x2 comma x3, an ordered triad where the elements x1 comma x2 comma x3 belongs to capital R. If x1 comma x2 comma x3 belongs to capital R, then we can say that the negative of all those real numbers are again real numbers. That is how minus x1 comma minus x2 comma minus x3 belongs to capital R. So that minus u bar is equal to minus x1 comma minus x2 comma minus x3, and this belongs to R3, and minus u bar is equal to let us take what is u bar plus minus u bar, and this we can see that u bar plus minus u bar is equal to x1 comma x2 comma x3 plus minus x1 comma minus x2 comma minus x3, and this is further equal to x1 plus minus x1 comma x2 plus minus x2 comma x3 plus minus x3. This we could write by using the property of addition of two vectors in the set R3, and this is nothing but equal to 0 comma 0 comma 0, an ordered triad of all zeros, and this is denoted by 0 bar. That is how u bar plus minus u bar is equal to 0 bar. We can also prove that minus u bar plus u bar is again 0 bar. So the axiom 4 of vector space is satisfied in the set R3 over the set R. Now the step 5. The step 5, we want to see whether the commutative axiom with respect to addition is satisfied in the set R3 over the set R. For that, to prove that, let us consider two vectors u bar comma v bar in R3. As they are in R3, they should be in the form of ordered triads. So u bar is equal to x1 comma x2 comma x3 comma v bar is equal to y1 comma y2 comma y3 for the all the elements in these triads, that those are x1 comma x2 comma x3 y1 y2 y3, all belong to the set capital R. All those are real numbers. Then u bar plus v bar is equal to x1 plus y1 comma x2 plus y2 comma x3 plus y3, and this is further equal to, I have replaced x1 plus y1 by y1 plus x1 and x2 plus y2 by y2 plus x2 comma x3 plus y3 by y3 plus x3. That means I have used the property of commutative axiom in the set capital R that we have seen in the prerequisite topic 1, wherein I said that capital R is a capital R has both vector addition and scalar multiplication defined in it. That is how I have taken the vector addition property with respect to commutative axiom, and here I have used that, and we could prove that u bar plus v bar is equal to v bar plus u bar. Hence the axiom 5 of vector space is satisfied in the set R3 over R. Now step 6. In step 6 we want to prove that the scalar multiplication is closed in the set R3. That means R3 is closed under the scalar multiplication. Scalar multiplication is defined in the set R3. So for that we need a vector and a scalar. So to prove the scalar multiplication in R3, we are taking a vector u bar is equal to x1, x2, x3 in R3 and a scalar c in R. Now consider cu bar, and that is equal to cx1, cx2, cx3 by the definition of scale. How could we write this? This is the scalar multiplication in the set R3, and by wherein cx1, cx2, cx3 are the elements of R. Therefore, axiom 6 is satisfied in R3 over R. Now, let us move on to the next step, that is 7th one, in which I am taking 1 belongs to the element 1 belongs to R, the real number 1, and u bar is equal to, I am taking it as x1, x2, x3, which is in the set R3. Now 1 u bar is equal to 1x1, 1x2, 1x3, and this is equal to x1, x2, x3, which belongs to R3. Now therefore axiom 7 of vector space is satisfied in the set R3. Now the step 8. Here I am taking 2 scalars and 1 vector u bar. Now consider c of du bar, and that is equal to c times dx1, dx2, dx3, and this I could do by the scalar multiplication in R3 by the step 6, using the step 6, and this is further equal to c times dx1, c times dx2, c times dx3 by the same reason, which is the scalar multiplication in R3, and it is further equal to cd times x1, cd times x2, cd times x3, and this we could do by the associativity in the set of real numbers, or this associative axiom with respect to multiplication in the set of real numbers. And taking cd out, that outside, cd times x1, x2, x3, we can write like this by using the scalar multiplication which we have proved in step 6 in R3. So finally c times du bar is equal to cd times u bar. By this we can say that axiom 8 of vector space is satisfied in R3 over R. Now it's the turn of step 9. The step 9 means the distributive laws we want to verify now in the set R3 over R. Let us take a scalar c from R and 2 vectors u bar, v bar from R3. And as u bar, v bar in R3, we can say that they are ordered triads, and hence I have taken u bar is equal to x1, x2, x3, and v bar is equal to y1, y2, y3. Now u bar plus v bar is equal to x1 plus y1, x2 plus y2, x3 plus y3. Now c times u bar plus v bar is equal to, by the scalar multiplication in the set R3, we can write this as C times x1 plus y1 comma C times x2 plus y2 comma C times x3 plus y3. And this is equal to cx1 plus cy1 comma cx2 plus cy2 comma cx3 plus cy3. And this is what this we could do by the distributive law in the set of real numbers. And then it is further equal to cx1 comma cy1 comma cz1 is one vector added to another vector cx2 comma cy2 comma cz2, and this we could do by the addition of two vectors in the set R3. And now by using the scalar multiplication in the set R3, we can write these two vectors as c of x1 comma y1 comma z1 plus c of x2 comma y2 comma z2, and these are nothing but cu bar plus cv bar. And finally we could prove that c of u bar plus v bar is equal to cu bar plus cv bar. And the last step, that is 10th one, here I am taking two scalars from capital R and one vector x1 x2 x3 from R3, and C plus D times U bar is equal to C plus D times x1 comma x2 comma x3, and this we can C plus D we can multiply to each of the element in that vector by the scalar multiplication in the set R3, and which we have proved in step 6. So this is equal to C plus D times x1 comma C plus D times x2 comma C plus D times x3, and this we can write as cx1 plus dx1 comma cx2 plus dx2 comma cx3 plus dx3 by the distributive law in the set R. And this is further equal to cx1 comma cx2 comma cx3 plus dx1 comma dx2 comma dx3 by the addition of two vectors in the set R3, and this is further equal to c times x1 comma x2 comma x3 plus d times x1 comma x2 comma x3 by the scalar multiplication in the set R3 by the step 6. So this is finally equal to cu bar plus du bar. So finally we could prove that c plus d times u bar is equal to cu bar plus du bar. So by the step 9 and by the step 10, we can say that the distributive axioms are satisfied in the set R3 over the set R, and hence we can, by the steps 1 to 10, from the steps 1 to 10 we can conclude that R3 is a vector space over the set R. This is the first example I have given to you for the vector space. Now let us see what is the example for the vector space in the example 2. For n greater than or equal to 1, for small n greater than or equal to 1, that means n taking values from 1 and the next values for n will be 2, 3, so on. So if that means we will get, if n is equal to 1 we get capital R, if n is equal to 2 we will get R2, for n is equal to 3 we will get R3, and so on. So in general the space Rn, where n we are taking as greater than or equal to 1, then Rn is a vector space over R. So in this R3 also is included, come in this, and that R3 I have proved as a vector space in the example 1. Similarly, you try at home taking R2 and prove all the 10 axioms of the vector space, and in Rn also taking n tuples as vectors, and we see whether all the above 10 steps are all the 10 axioms of vector space are satisfied in Rn over R. These two are exercise for you. You can verify for not two, in fact 3. You can have three uh, problems are 3 proofs to be taken for exercise, and they are for n is equal to 1, for n is equal to 2, and for n itself in general. So next, the example I have given is V is the set of all m by n matrices with real numbers as entries. So in the next example I have taken in example 3, V is the set of all m by n matrices with entries as real numbers, with elements as real numbers. If addition in V is defined as usual addition of matrices, so in to prove that V is a vector space, we need two operations. One is addition and the other one is scalar multiplication. So for addition in V, I am taking the addition of matrices, and for multiplication in V, I am taking the scalar multiplication of a matrix by a scalar. That multiplication of a matrix by a scalar, that we can call as scalar multiplication of a matrix. That those two operations as addition operation and scalar multiplication, we can show that V forms a vector space over the set R of real numbers. And the next example, as example 4 I have taken, is the set of all polynomials of degree at most n. That means n less than or equal to n. And n should be greater than or equal to 0, and it should be less than or equal to n. For such set of polynomials where each polynomial is of the form p of t is equal to a0 plus a1t plus a2t square plus so on plus an power n, where a0, a1, so on, an and t are real numbers. If q of t, let us take another polynomial, q of t is equal to b0 plus b1t plus b2t square plus bnt power n, where b1, b2, so on, bn are real numbers, and t already we said it is a real number. Now let us see what is sum p plus q, sum of two polynomials. How is it defined? P plus q of t is equal to a0 plus b0 plus a1 plus b1 of t plus so on plus an plus bn of t power n. And the scalar multiple Cp is defined. This is the addition of polynomials defined in the set capital Pn. The set of all polynomials we are denoting by Pn here, Pn. So addition we have defined like this. Now let us see how the scalar multiplication of polynomials is defined in the set of polynomials Pn. And that is like this. That goes like this. Cp of t is equal to c times p of t, and this is defined as ca0 plus ca1 times t plus so on can times t power n. And p plus q comma cp are polynomials of degree less than or equal to n. We can see here p plus q will be the same degree of p or q or less than of it, and cp is also a polynomial of degree less than or equal to that n. The zero polynomial with a0, a1, so on, an all as 0, all the coefficients as zeros, that polynomial acts as the zero vector. Thus we have addition, we have scalar multiplication and the zero vector also in the set of polynomials Pn, and that is how we can say that Pn is a vector space. So thus Pn is a vector space over the set of real numbers only. Here also the set of scalars is the set of real numbers, that we have to understand. Next, fifth example. If D is either the set of real numbers or some interval on the real line, Let us take capital D as the set of real numbers, or it can be some interval on the real line, open interval or closed interval. Then the set V of all real valued functions, then the set of all real valued functions is a vector space over D with the usual addition and a scalar multiplication of real valued functions. So these are the 5 examples that we can give for the set vector space. So with this I close the class now, and in the next class, in the next lesson, we can go through the properties of vector spaces and other things that are included in the first topic of the unit 1. Okay.